Video, I want to say a few things about predicate logic, also called first-order logic. As we mentioned last time, in predicate logic, there are variables and quantifiers. The two quantifiers we're going to be looking at are the universal quantifier and the existential quantifier. So universal, sometimes also read for all, is typically written as an upside-down A, like this, and the existential quantifier that exists is typically written as a mirror E. So here are some examples in which we use those two quantifiers. They always go with a variable. For all x, if somebody is human, then they're mortal. So all humans are mortal. Over here, there exists some x such that x is human. There's a human. Now, again, these are variables. And so let me point out a few things, a few similarities between these variables to those that we know from programming languages. And so in both of these cases, we can assign something to these variables. In the first case, we can assign anything from our domain because of the universal quantifier. If the domain consists, like, say, the people in our class or ancient Greek philosophers, then, whatever we assign to x, this statement has to be true. So we can pick any, and the statement is going to be true. Versus over here, in order for this thing to be true, we have to find just one x from our domain, one entity from our domain, for which we can assign this thing true. Another thing that we will see later today is scope. So obviously these two are in a different scope. So whenever you have this universal quantifier x and colon, that's kind of like the scope of this variable here. But again, we'll see more about that in a little bit. So let me introduce the 4 new rules of inference that we have in addition to those that we have seen when we looked at propositional logic. So just like for propositional logic, for each quantifier we have an introduction and a removal rule. So let's have a look at universal introduction. So over here, we want to prove something, some property that holds for any element in our domain. And so the way we do this thing is we sort of like say, all right, pick an entity from our domain, any entity, it doesn't matter. So a lot of times the keyword here is arbitrarily chosen. So have an arbitrarily chosen entity from our domain and let's call it C. And then if you can prove that something holds for an arbitrarily chosen C, let's say the property P, then since it is arbitrarily chosen, you can write down for all x, P of x holds. So that is universal introduction. Universal elimination is stuff that you do all the time. We have a universally quantified formula, and you can pick any item from the domain and assign it to it. So you can instantiate it to any constant in the domain. So typically we name things. We don't have arbitrary, which obviously that's what we do. So that's universal elimination, again, something we do on a pretty regular basis. Existential introduction, again, if you know something holds for a particular item in the domain that we named C, like Socrates, then we know that, if the property holds for an item, there is at least one item in the domain for which the property holds. So notice that we sort of like generalize this thing a little bit. We don't want to name names here. We just simply say, well, there's something. We know that. Or some item, some person in the domain. Then we have existential elimination. That's also a kind of really interesting way of proving things. If we know that there's at least one entity in our domain for which the property holds, then what we're going to do is we can give that entity a name. So the police do that quite a bit. So suppose a crime has been committed. They don't know who has done it, but a lot of times they then give that person a name. So if they know the person is male, they call them John Doe, and if they know the person is female, they would call her Jane Doe. So they know somebody did it, but they just haven't figured out who it was. So they just give that person a name. So that's existential elimination. Again, something that we do quite a bit and that stuff that you have seen before. So what I want to do now is, or in a moment, we want to give a proof. So we want to prove using just the rules of inference that we have seen in this presentation and the prior presentation to show that if everything that is small is a cube, and if there is something that is not a cube, then there is something that is small. Okay, so notice that these two x's are different x's. There's different scope. This x goes from here to here. This x goes from here to here. So if these two are true, then there is something that is a cube. So I'm going to have a separate narration, again, using this Fitch-style proof checker to show you the proof. So that'll be in the next presentation. I will see you then. Bye.